why invariance appears when you least expect it. Let's talk about the following experiment. I'm going to fix a point V1 at a right vertex of an ellipse and a point V2 at the left vertex. And I'm going to fix a third vertex to form a triangle somewhere on the boundary of this ellipse. So I can move this point around. So now I have the triangle V1, V2, P of t. And I can compute, for example, the orthocenter of this triangle. It's right there, x4. Orthocenter is the point of concurrence of the altitudes of a triangle. Currently, this triangle is obtuse, so its orthocenter lies outside, right? So if I perhaps animated this point PT over the border, I would get this phenomenon. Okay, now it turns out this thing is an ellipse. All right, it also turns out that wherever I place my 2 points V1 and V2, so let's go ahead and choose another situation here. Let's put V1 over here. I'm going to put V2 over here. It doesn't matter where I place these 2 points. The locus of the orthocenter of fixed V1, fixed V2 on the ellipse, and the third point sweeping the ellipse is always an ellipse. We just observed that. So let's animate P of t again. So that's quite interesting, right? It's going to actually cross at some point 3 axes. Let me change, for example, the position of V2 now. Let's put V2 somewhere else. Let's put V1 somewhere else. There you go, V1 and V2. No, they're here. They're almost vertical. It doesn't matter wherever they are on the ellipse. Okay, wherever they are, wherever these two guys are, you get an elliptic locus. Okay. Now the second interesting remark here is that whichever ellipse is generated, it's always axis aligned with the original one, but upright in the sense that the major axis of the locus is vertical and the minor axis is horizontal. Okay, now if this were not enough, here's a really cool result that I wanted to share. So imagine V1, which is somewhere on this ellipse, is represented as, let's call A the major axis and B the minor axis. So V1 is A cosine of T1 and B sine of T1, so that these are the coordinates, the parameterization of V1. So I'm parameterizing it with respect to T1, and V2 is parameterized similarly, but with respect to a T2. So V2 is A cosine of T2, comma, B sine of T2. Now here's the interesting remark. As long as T1 plus T2 are constant, so consider all pairs V1 and V2 such that T1 plus T2 is constant, the ellipse generated is exactly the same one up to translation. So this is what I'm going to do now. I'm going to actually move, move my points to a particular position, and I'm going to move this point around such that if this one is T1 and I choose a particular sum T1 plus T2, so that sum is going to be chosen to be 74, for example, I'm just going to move both points so that that sum is preserved. So if I do that, for example, if I do that, the resulting ellipses are identical. They're just identical. Okay, so now let's change that, the value of that sum. So I'm keeping V1 fixed. I'm just changing the value of T1 plus T2. Again, I get identical ellipses as I move these points around. Let's now place, for example, P1 exactly at 90 degrees over here, and sorry, I placed P2 there. Let's leave P let's leave P of t over here. This is just the point that sweeps the locus. But I'm going to place P1 of V1 at let's place it at minus 90, so it's over here, and I'm going to make the sum of the two guys to be equal to, say, so this one is at minus 90. I'm going to make this sum t1 plus t2 be equal to 0. Okay, so if the sum t1 plus t2 equals to 0, it means that one is opposite from the other. So I get this nice symmetric situation whereby the x4 locus is an ellipse tangent at the top and bottom vertex of the original ellipse. So what I'm going to do now is I'm going to move v1 around the ellipse, but I'm going to keep the sum t1 plus t2 constant. So v2 is basically dependent on the motion of v1. So let's do that. Look at what happens. I'm basically translating the exact same ellipse to the side. Its area doesn't change, its axes don't change. Okay, so this is a first phenomenon. Now let's place T1 back to the 90-degree position. I'm going to place K at some intermediary sum. T1 plus T2 now is equal to 20. So my T2 is equal to 20 minus T1. So this is what you got. All right. Now as I move T1 around, I'm getting a translated ellipse. Now this translation is not purely horizontal, it's going up and down, but it's the exact same ellipse with this exact same area. Okay, now let's increase that sum to, say, 40 degrees now, and let's watch that motion of the ellipse. It goes up, it goes down, but it's the same ellipse, no change. Let's make this difference now be 90 degrees. So now I get V2, so T1 plus T2 is equal to 90, which means that T2 is trailing, or is actually 90 degrees minus whatever T1 is. Okay, so as I move P1 around, I get this. It's the same ellipse, no change. It's just getting translated up and down. Now, where is the center of this ellipse? We haven't calculated it yet. What is this translation going to look like? What's the principal direction? What's the general direction? Is this always a straight line? Is this translation a true straight line? It looks like it is. Okay, it doesn't look like there's any curve to it. So what are the characteristics of, an experimental thing we've seen is that the area of, the maximum area achievable is when the difference is exactly 0, when it's 180 degrees. So when you get 180 degrees between V1 and V2, and you do this kind of a thing, let's debox it, let's move this guy around, the ellipse doesn't change, and it's the largest possible ellipse, is when V1 plus, so T1 plus T2 is equal to 180 or pi, meaning that T1 is pi minus T2, or T2 is pi minus T1. And when that distance is 0, when the sum is equal to 0, so they're symmetric numbers, this is the smallest possible ellipse that can be generated. So if my sum now is 10, I get a slightly bigger ellipse. If my sum is minus 10, I get the same size ellipse as I did for the 10 case. Okay, now this looks crooked, but this is just an optical illusion. If I move this around, you're going to see that this ellipse has axes that are perfectly axis aligned. Okay, so it's always a translation of an axis aligned ellipse. Okay, so that's what I have.